Hello, my name is Favour and I'm a PhD candidate at Stanford. Today I'll be presenting our recent work entitled An Explainable Geometric Weighted Graph Attention Network for Identifying Functional Networks Associated with Gait Impairment. Parkinson's disease impacts 10 million people around the world, with an estimated economic burden of 52 billion each year. PD is highly associated with an increase in aging and a decrease in motor function. The onset and progression of symptoms in PD vary significantly. A hallmark neuropathological feature of PD is the degeneration of dopamine-producing neurons in a region of the brain called the substantia nigra. These neurons produce dopamine, a neurotransmitter that plays a crucial role in regulating motor function and movement. As more of these neurons become non-functional, there's a corresponding decrease in the amount of dopamine available in the entire brain, severely impacting its healthy functioning. PD progression is associated with changes in motor symptoms such as tremor, rigidity or stiffness, postural instability, and bradykinesia or slowness of speed. Postural instability in PD can be evaluated using the MDS Unified PD Rating Scale, the gold standard clinical assessment for PD diagnosis. We aim to predict gait impairment scores from functional connectomes by using a graph attention-based model that can encode and explain discriminative brain network attributes. Functional brain network analysis of individual gait impairment severity has been used to model and predict PD diagnoses. However, they typically focus on only a binary diagnosis like PD versus control, or only use sensor and vision-based technologies to quantify PD symptoms. In contrast, our work performs multi-class predictions using functional brain network analysis and correlates our results with clinically relevant interpretations. We solve the following challenges: individual variability in disease progression, sparse and imbalanced clinical data sets, and explaining our findings. Our first solution addresses challenges 1 and 2 by using Riemannian manifolds to project and encode high-dimensional functional connectomes for pairwise comparisons. In a total set of n samples, for each sample P, we define an FC matrix of D by D ROIs. While FC matrices contain useful information about correlations between ROIs, standard analyses typically only take into account spatial information and fail to capture rich interactions in the underlying geometry of functional brain networks. Each FC matrix contains properties that allows it to be represented as a semi-positive definite matrix, through which we can apply a transformation to our training dataset to project each sample to a non-Euclidean space. We can then perform non-Euclidean operations like using Riemannian distance metrics as a method for comparing complex similarity between connectomes. Our second solution aims to mitigate sparse and balanced issues with sample selection by using an informed learner to equally represent all minority classes on the training set, building on previous works like RegGNN by Martin Hannig. Using our connectomes on the Riemannian manifold, we leverage the graph network of each sample, where each ROI is a node connected by a set of vertices and edges. Each edge holds weights that correspond to the correlation coefficient, or strength between two ROIs. For each sample, we extract centrality measures such as degree and eigenvector centrality that define each node or ROI importance and connectivity relative to the global network. We use these measures as features to predict the samples that most strongly correlate to a specific class using linear regression. We conduct a stratified approach to select the top case-central training samples per class. Then we oversample those sub-selected samples to balance out minority classes in the training set. This allows for a balanced training set where each sample is represented as a graph and underlying node attributes. Our third solution predicts the gait impairment score using a neural network of GAT-V2 layers equipped with attention-based edge-weight message passing. This allows for local and global influence while learning. It also outputs trained attention coefficients used to create explanation masks per sample and per class that can be later visualized. We collected and pre-processed a dataset from the Stanford School of Medicine consisting of baseline resting state fMRI connectivity matrices. Each connectivity matrix has 165 regions of interest and is associated with the participant's MDS UPDRS gait scores, ranging 1 through 4. We train our model for multi-class classification using the weighted adjacency matrices as the feature, averaged over 100 trials, and optimized our hyperparameters using NNI-Learn. Our method, xGW-GAT, outperforms state-of-the-art models like BrainGNN, BrainNet-CNN, and Standard GAT by up to 29% improvement in AUC. We also demonstrate that our performance is enhanced by up to 9% while using the stratified learning-based sample selection method. This supports that our work minimizes random uncertainties introduced by individual graphs or connectomes while retaining high classification accuracy. Additionally, we provide results for attention-based explainability where we see clinically relevant findings. We use 9 predefined networks that correspond to several functional, cognitive, and motor functions as studied heavily in literature. For example, we observe rich interactions decrease significantly for the mild cohort within the cerebellar and salience networks. Existing findings show PD is positively associated with the severity of cognitive deficits and neuromotor control for inter-network and intra-network interactions within the salience network, cerebellar lobules, and visual network. Likewise, we observe significantly lower connections within the cerebellar network and visual network for the moderate and severe cohorts. We see fewer and weaker connections within the sensory motor network in these cohorts. Prior studies show functional connectivity losses within the sensory motor network are correlated with disruptions in regional and global topological organization for sensory motor areas for PD patients, resulting in loss of motor control. Lastly, for participants with mild, moderate, and severe gait impairment, we notice abrupt disruption within the frontoparietal network, corresponding to less attention salience within those regions. The frontoparietal network is known for coordinating behavior, and several studies observe an association between connectivity alterations in this area and motor deterioration. In conclusion, we provide a novel benchmark for recovering patterns associated with categorical PD and gait impairment. We integrate edge attention encoding to represent full pairwise interactions in functional connectomes. We also provide interpretable functional network clustering for neurological analysis. And lastly, we show stable results for sparse and imbalanced clinical datasets. For our future work, we will do additional external validation on a larger public dataset, conduct rigorous sensitivity and specificity analysis of the salient networks, and do additional attention mechanisms and interpretability. Thank you to the MICCAI 2023 team, our Stanford collaborators, and our funding supporters. Thank you.